right before lunch, so that's a positive. So you're eager. That means I can't be up here forever and a day. Thank you so much for the introduction. Thank you all so much for being here. One thing I have the opportunity to speak. I think it's awesome space. And yeah, like, oh, people want to hear about roots and common things. That's interesting. Okay. See, the title of my talk is Roots and Resilience. We really want to talk about driving community impact through comic breeding at the Jackie Joyner Kersee Center. Um, what I really hope you pull from this is that we're really just at the beginning phases of some of the work that we're doing. And it's going to be up to a lot of people in this room and the people out of St. Louis areas. We continue and we really want to share input and your involved. So, a little bit. I found agriculture as a high school student in Huntsville, Alabama, and I saw this and was like, I love it. I want to do it. Got to do it. Have to do agriculture. For anyone who has not seen this, this is tissue culture. So plant cells, they form these very specialized structures, and then we can use tissue culture, hit them with a bunch of things, and it's not like, oh, okay, let me get rid of the script I had. It says I should become a leaf or I should become a root. And they basically are pliable. They can become lots of different pieces of tissue. So we take this single piece of tissue in the lab, cut it up, and then it becomes on that third picture. Okay, see that. It becomes hundreds of plant structure in a petri dish. Saw that as a junior high school. Was like, yep, so agriculture, you gotta do it. In the world. Here. And so I went and I was gonna tell my grandma I found agriculture. She was like, yeah, I'm always like 9 grandkids. I would hope. I was the hope of the first generation of grandkids. And she's like, oh. I didn't really understand what she meant by that at the time, right? But looking at the historical context, my grandmother would have grown up in the 1940s, and it would have been around the time that we saw one of the steepest declines in Black land ownership in the country. And so this idea that she was telling me wasn't that agriculture didn't have the promise to be this amazing technology in the future. She was saying the way it's been applied in this country has a history of secluding certain people. That's what she was telling me, or excluding certain. So kind of keep this in your pocket because I think this idea was something that changed my idea about agriculture and forced me to see it a little differently going into my agricultural career. So resident, all right. My name is Antonio Brazelton, as I mentioned, I'm from Huntsville, Alabama. I was a USDA 1890 scholar, so NRCS, Federal Government Faith Media School. I took SE University, got my master's in environmental science, my soil science, and then on to Iowa State to get my master's in genetics. And then I came out to St. Louis and started working here at Bayer. I was a genomics IT product manager, so IT systems around the genomics space at Bayer. And then I guess I was bored, so I was like, well, okay, I can be a dad now. I became a father. It's my son Benjamin here in the picture. And then I got bored again. It was like, should we go back to school? Yeah, we go back to school. And so I started at WashU in 2021. I joined the Top Roots Lab. Learn a little bit more about that. But basically, we take pictures of roots, right? Why would that be important? Find out. And then more recently, I became senior coordinator for research partnerships at Jackie Joyner Kersee Food, Ag, Nutrition and Innovation Center. So I'll be focusing primarily on those last few pictures, some kind of my journey thus far. So we'll start with the JJK. Right? The Jackie Joyner Kersee Food, Ag, and Nutrition Innovation Center is a unique public-private partnership between 4 partnering institutions. It's the Jackie Joyner Kersee Foundation, pretty St. Louis, the University of Illinois, Urbana-Champaign, particularly their extension arm, the Lansdowne Up nonprofit, which is an awesome workforce development nonprofit over in St. Louis. And then finally, the Danforth Plant Science Center, where my lab is housed. So it's a really interesting synergy between the organizations where we really get the opportunity to focus on food, nutrition, plant science, but also overall wellness. So Our purpose is collaborating to inspire youth and families in East St. Louis and beyond, using urban agriculture, physical activity, and constructive youth development. And so our vision is really to become a nationally recognized innovation center. Right? Our role is kind of at the centerpiece of that, as well as my colleagues' roles. We're really building out East St. Louis as a national center for urban ag, food innovation, entrepreneurship, career. So most of what I end up doing as coordinator for research and partnerships is around our new 70-acre innovation campus. We got 70 acres that we have. It's roughly 70 over in the East St. Louis area. It's comprised of a few separate spaces. This is the first phase build out. It's roughly 2,400 square feet. This innovation center, which you're seeing right here. You want to see that on the screen? You can't see it.
Oh, no, not the pointer.
Okay. It's okay. But this innovation campus here is kind of blown up is our new 24,000 square foot innovation center. So it's going to be an awesome space for teaching students. It's going to have lab space, a nice culinary kitchen. Space is really for us to focus and harness our opportunities to build sort of that child development space. That's in the mix right along with our outdoor market and research gardens, which are right here, these sort of 4 boxes. I mean, those are really going to be focused on growing crops in the city, right, and kind of teaching people how to grow crops in the city, but also research space, right? And so I talked about our partners, the Info Plant Science Center, as well as the University of Illinois. So we have researchers that will come have their research gardens in the space, but also be doing that work alongside community. So the idea is really to have this interwoven community and research opportunity in space that our students and the communities benefit from. There's some major ag demonstration facilities where a lot of my work and some of my colleagues' work will also be going on. We have a greenhouse that I'll talk to them about here at the end of the talk when we're doing some of the Collards imaging. It's 11,000 square feet. It's the first one in the United States, second one in North America. It essentially allows us to grow throughout the year without being constrained by some of the weather issues of Tennessee here in St. Louis, right? We have these decoupled aquaponics spray containers, the 240 containers that are completely refrigerated. We're able to do aquaponics on the bottom, on the inside of the container, it's controlled. But then we also have above container space where we're growing plants. And so using the decoupled system to do some major work in separating some of the plant and fish spaces. And then we have our Jones Park greenhouse where we end up producing a lot of lettuce and other things for the community. So also ag demonstration facilities. I'm going to focus primarily on this passive solar greenhouse later on in the talk. But these are some of the major spaces that we will focus on and that you'll see throughout the talk. So I'll give you a little bit of background about myself and the Jackie Joyner Kersee Food agriculture, right? Culture. If you've been to an ag talk anytime between now and the last 20 years, you've probably heard the statement, by 2050, we'll begin to meet the nutritional needs of about 10 billion people, right? Show of hands, you've heard that statement, some of that statement. So when I was starting junior year in high school, this is the first thing it's a lot of folks, right? And to be honest, it's kind of phrased as a one-part question, right? But I see 2 equally important problems, right? One of those, which is the primary focus of my discipline, is food production, right? We need to produce more food to ensure that we're feeding those 10 billion people by 20. The plant sciences, biology tends to focus on but I also think it's a problem. We need to allow more people more access and the ability to make sovereign decisions over the food that we already produce. Right? Those are 2 very separate ideas, but I find myself somewhere in the middle of how do I produce more food, but also allow opportunity and access for people to make the type of sovereign decisions over when they eat and how they control their own systems of behaviors. And so because I see 2 equally important problems, I think the end of that statement on we need to feed 10 billion people by 2050. The focus shifts a bit, right? So not only do we need to feed uh, 10 billion people, we need to think about where those 10 billion people are located. What are the socioeconomic issues, things that are financially affecting those 10 billion people, right? And the truth is, 2/3 of the world's population of that 10 billion we're talking about will reside in urban areas, right? If we think about just the US, 80% of the population currently lives in urban areas. So we're talking about more people now that will essentially be occupying those urban areas. That becomes a problem for food access, right? Because essentially most of your food travels about 1,500 miles before it ever reaches your plate, right? That's a trip from New York to Miami for every meal that you have, right? And so essentially we need to be focusing on ways that we can produce food in and around the spaces where people are currently located, right? By and large, urban agriculture has been really good for that. I see a few urban farmers in the room just from some of the spaces that I operate in. And by and large, we think about urban agriculture as an opportunity to sort of shift some of those narratives around where food is produced that who has access to, right? Uh, Actually, these pictures are, at least two of them are taken from farms here in the city. One is from Urban Harvest, any urban farming or urban harvest over in the room. So one is from Urban Harvest, the other is from Confluence Farms, that's friend. Uh, and so there's a range of different growing opportunities here, but I think urban ag is really changing what that landscape looks like in terms of how we get food to people in the spaces that they're currently in instead of it having to travel. The larger issue is it's not easy to grow food in the city, right? I think those same farmers that raise their hands would tell you that there's a ton of challenges that we face in terms of growing food in urban space with right? Some of those are access and like social issues. Others are just environmental issues that constrain space, right? We think about things like soil contamination, right? Last I checked, a lot of the conversation that growers is you should probably grow in raised beds if you're unable to check your own soil, right? But that tends to be a constraint that most folks have because there's not cheap. So soil contamination is an issue. Soil compaction is another issue that we deal with, right? Because these are built spaces, the amount of soil space and soil differentiation is just not there, right? These are places where we've taken large scale equipment to build roads, build infrastructure, and then because of that, growing spaces, the soil is just different, right? It's more compacted. We also see issues with drought and water access. So because the soil is compacted, we're not seeing the water leaching through the soil like we normally would, beyond just some of the issues around who has access to water in the city, right? Clean water is some issues, right? So these are all challenges that urban farmers and people growing in urban space tend to deal with. And by and large, if you think about it, go with me here, we're talking about roots. Okay, think about it. Go with me, right? And so in each of those major issues in terms of the environment that we talked about, roots play an important role, right? Not only are they holding the plant to the ground, they're securing the plant, but they help the plant adapt to multiple stressors. And so normally we talk about like plants, stress. We're talking about the above part, but really the roots is the first major appendage to develop are a place that we need to maybe spend more time. Just saying. So in my lab, we study the hidden path of plants. Who else been on the Zoom call? Usually we see people in a video in the Zoom call, they look like this, they're nice played up, shirt, tie. I don't know about y'all, I know I did. Some of us came looking like this. Some people had on sweatpants, some people had on underwear. Some people, we really didn't know what people had on. And so my lab at the National Science Center is really interested in figuring out what are people doing, like what are plants doing underneath the tables? Can't we see, right? And we focus on a range of different tools to be able to study that. One of the major tools is going out and digging holes in the ground. So this is a picture from Weaver, 1919, one of the sort of godfathers, if you will, of exploring plant roots. And in 1919, published a paper about how he went out and they were digging holes in the ground to form a major waste studies, right? Unfortunately, we've come a long way. There's a lot of different tools we can use now. The description you're seeing from A to E is sort of the way you read that. A is like the reality of what roots look like in the soil. B, C, D, and E are ways that we can study roots. So we can go out and dig a trench, sort of like what Weaver did. We can take soil cores, where we go take like a pipe and you stick it in the ground and pull it up and see what roots are there. We can use mini rhizotrons, which are these cool cameras that we can stick into the ground and pull out as we please, right? That take images of the roots as they're growing. And then we can go and be probably one of the most destructive things out of this list of things. We can go dig the plant up, right? I'm primarily going to talk about digging the plant up, but the colors you see on the side or on the picture show us how much of the root system we're actually able to see based on the technique that we use. And this was published in 2020. By and large, the closest to phenotypic reality is still trench excavation, right? It's still us going, digging a trench in the 12 feet and actually watching the roots grow in soil gives us the best picture of how they grow. But we're also able to pull some information from the last method. So digging root cracks. So that's essentially what I'll be talking about further on in the paper. Yeah, we're going to talk about root crown excavation particularly, and this thing called root system architecture. So keep that in mind. Root system architecture is influenced by these genetic and environmental factors. Essentially, it is just the plant deciding where should I put roots and what time should I put. Right? If you think about it, plants are constantly pulling water, they're pulling nutrients from the soil. They don't have eyes, they don't have mouths, they are essentially needing to sense in millimeter intervals, like, should I grow this way? Is there water this way? No, don't grow that direction. Is there nutrients this way? Grow in that direction. And so my lab is really interested in us being able to capture these moments where plants decide to put roots down, right? And what those phenotypes look like, right? What those differences of how the roots grow look like. The important part about this is we can use what those differences are to build what we call idiotypes. And essentially, these idiotypes are the idea that there are ideal root shapes and root sizes for different environments. So by and large, the normal focus of this sort of thing is what do roots look like in a conventional agriculture system, right? We're out in a field somewhere, they have 4 to 6 feet to be able to grow, or the depth they want to be able to grow. We're not really, or usually talking about how these roots should be safe for urban spaces, right? Where we're talking about farmers that may only have a hard pan layer of a couple of inches before they hit clay that's indestructible, right? And so the idea that we really want to focus on is how do we breed these crops so that they have root structures that are best for this urban environment now, right? And can we use it, in a participatory manner where we're breeding with farmers above ground for the traits that they like steaks wonderful, with traits that are best for the roots, best for the soil. So some kind of way I decided, oh, this is an awesome question to ask. Let's do that. It seemed like it would be hard at all. And so I proposed over here that the nursery family is an ideal space to start working on finished roots for urban agriculture. Shout out to DJs. And I think this is the mustard family is an awesome, awesome opportunity of genetic diversity and species diversity, right? That we can see pretty easily. It's also related to some of our plants that are most experimentally applied, right, around the specific antibodies. I think the mustard family is a good place to start. Well, why mustard, right? All the things or something. One is the selection for mustard is already giving rise to a bunch of different types of plants, right? So when we think selection for flower bud stems, we're talking about broccoli, right? Selection for lateral roots gave us Brussels sprouts, right? Selection for terminal leaf buds gave us cabbage. Selection for leaves gave us kale and collards, right? So focusing on brassica oleracea as species gives a really good opportunity for broad application of some of the root traits that we can integrate. So in this family, to decide, do I want Brussels sprouts? Do I want broccoli? Do I want cabbage? And I focused on collards, right? Who already said collards? So, me, collards, hair collards, okay. Right. Oh, y'all got a family in Mississippi? She's what I hear. Say this one. I'm a country boy from Alabama, my state. And so collards is something I grew up with. Collards is something that I grew up growing with my grandparents, picking with my mom, my dad. So it's a kind of a plant that was very close to me anyway. But then as I was starting the PhD journey, I was looking at what crops do my urban farmers, do people in the St. Louis area grow. And some of the work by some of this early master's work was kind of surveying urban farms and urban gardeners in the St. Louis area for gateway greening. And one of the things that they grew a lot of was collards, surprisingly, right? And so I said, hey, collards is a good space within mustard family to focus on. And so I kind of talked more about policy going forward. So right around the time I was figuring out I wanted to work in collards, the Heirloom Collard Project had released this awesome project around giving recognition to heirloom collard varieties, right? So I was like, okay, let's check that out, see what that's about. And essentially, if you didn't know, so there are over 150 different varieties of collard green. Most of those are held at USDA. Just in the green, they have a nice little library. So the Heirloom College Project is really about getting these seeds out of the hand, not out of the hands, but they're taking them off the shelves, right, at USDA and sort of rematriating them and giving them the opportunity to be recognized back in the hands of gardeners, farmers, folks that do seed work and seed breeding work. And so of those 150, they took 20 varieties and they said, okay, these are really diverse. If you look over at the picture here, there's a range of leaf sizes, there's a range of leaf shapes, there's a range of curling patterns, a range of colors, and all that is really just genetic diversity. Is what that is, since these are heirloom varieties. They come from places like North Carolina, Alabama, Georgia, locations where these seeds and these varieties were essentially saved by host families. Davis and Morgan were the geographers that really collected these seeds. Basically, they went to people's houses and were like, hey, I got some collards growing out in the backyard. They don't look like the ones we see at the grocery store. We have seeds. And by and large, people were like, yes. Okay. And so anyway, Heirloom Collard Project did a variety trial for these 2020. And basically, they sent seed out to about 250 different locations and said, grow these out and let's collect information, score them 1 to 5 on their flavor, on their disease resistance, their cold hardiness, which ones come up first, right? Small things like that. And so they published, this is still running actually, they published some of the data, and this is kind of scaled down. I don't know if y'all can see the font there. But I scaled the varieties down just to yield and vigor, right? So yield is essentially how much above ground portion that we eat are these plants putting out. And then vigor is how quickly they're growing into that above ground space. And so I ranked basically from those 250 sites, which varieties did the best, which ones did the worst. All the way over in the right-hand corner in green is Georgia. Have I heard Georgia greens before? So Georgia greens are the ones that I kind of falling back home on because they were Georgia greens. Most of the people I talked to were like, "I was going to Georgia." It was interesting though that of all the heirloom varieties, Georgia performing worse in terms of yield, but they're most widely grown, eaten, and most folks, outside of this variety trial, never heard of any of the other varieties. So I thought yield and vigor, because they're so strongly correlated to root trace, and there's no root data it'd be really cool to start to look at root traits for this population and see if there's any related traits that we can look for to begin to breed for. So now I got questions. Okay, right? And I don't know if you all can read this too, maybe a little on the screen, but the questions are like, are they really that different? Are the roots like just little straws that the plants are putting down on the ground? They're all the same size, they all look the same. It doesn't matter. Nobody cares about that. We're even like the above ground part anyway. And so the first experiment we really did was getting rid of the environmental portion, right? Let's just see what is packed inside these plants innately, which is the first experiment to talk about. And then finally, once we figure that out, can we go out to the field and test it and see if that holds true out in the field, which is the second experiment I'll talk about. And I promise I won't do this. I just need to show you a bunch of data with no real pictures, and there's lots of pictures. So the first thing we did when I got to the lab, like you got all this seed from these seed saving folks, go grow it in gel. So we have like these 2-foot gel containers that we grow these in. We give the plants everything they need, but we make it the ideal environment, right? Remove the soil and environmental factors. So what we should get is just the genetic pieces, right, for each of these varieties to see if there's differences. So we grew these seedlings out for about 15 days. And took images every 3 days. So 6 days, 9 days, 12 days, 15 days. It was a lot of plants. It was a lot of plants and a lot of time growing out of the greenhouse or in a controlled space in the greenhouse facility. But I guess still may work. So this is the process. Essentially, we grow those in these large tubes. Or we grow in those large tubes and we set them in this big fish tank. And we allow a camera to take pictures as the fish tank rotates. And so it gives us the opportunity to put together these 3D image stacks where the plants are still growing, they're still alive, and see what the roots are going. Over on the right-hand side are 2 separate varieties, 2 separate root systems, and you can kind of see the difference where like in 15 days, one of these varieties decided I should grow as deep as I can grow real quick. Another of these varieties was like, I should make real short, fat roots because this is not, this is not the ideal space, right? But the idea is we can take some of this and say, well, which of these root systems, which of these varieties is best for what we want to do in urban space. Right? So pictures, I promise pictures. These are 4 varieties that we'll focus on really quickly to see some of the differences in root shapes. One is forage collard, so this is essentially a cover crop that we look at. It is normally eaten by cattle, really deep, very well structured root system. The other is Fuzzy's cabbage collard. It's one of the purple collards that we look at in the heirloom collard variety trial. Awesome flavor. The other is William Alexander Heading. That one is more like a heading cabbage, like less colorful, sort of bland on the taste. And then finally, Georgia, which is, the normal variety that my farmers are used to seeing. I think the cool part about this is there's like some very small details that you can see just from the pictures, but just to focus on like 2 traits that are easy to see, we'll focus on depth and network convex area. There's 2 ideas to kind of figure out like how these roots are different, if they're different at all. So the first thing we'll look at is depth, right? Like vertical growing length for the roots. So over on the right-hand side, I guess my left, but over on the right-hand side of the screen, we looked at forage collard in terms of depth, how deep is it, and this is in millimeters. Fuzzy's cabbage collard, Georgia, and William Morris Heading. And you can easily see, so, see now the legend did print. But on the dark blue purple at the top is day 6. Day 12 is, day 9 is the lighter blue. Day 12 is the green, day 15 is yellow. So essentially, you take nothing else from this. It's that the forage cabbage collard ended up getting some really good establishing itself fairly deep by day 6. And so by day 15, it's the biggest thing out there, right? So in terms of disease pressure, in terms of its ability to sequester water and nutrients, it was like grow fast, grow quick, right? Whereas the William Morris Heading on the very opposite end is like, I'm gonna put out something real fast, and then whatever happens. It's working, but I want So that was one of the cool results we saw, was just that like early seed establishment ended up being really good for at least 15 days here for the seedlings. The other real quick trait that we look at is network convex area, and you can think about this as like how well the plant is spreading, right? So it's established a root in terms of its depth. How well is it spreading out? Where I thought it was really cool, so it's like wrapping a rubber band around the root system for a whole area. What I thought was really cool was 4-inch cabbage collard, right, was the deepest thing we saw in the gel imaging experiment in the previous slide. Fuzzy cabbage collard, not so much on the depth, but by day 15 in the yellow here, it is covering as much area this way as 4-inch cabbage collard is covering this way, right? And so when we're looking at varieties to select, we're like, okay, of these 20 heirlooms, let's take 5 and start breeding them in the field. We might be able to take fuzzy and say, well, since you're covering the same area in a soil that does not have the depth that our rural space has, maybe this is a good opportunity to begin looking at you as a potential parent for breeding. Maybe we set you up on a date. No, set you up with someone else. And so that's sort of what we began to look at pulling these traits apart here. If we put those two together, right, depth, network, convex area, so how deep were you, how much area are you covering something that's like this? This is, I promise, the worst thing that's been shipped. So this is a scatter plot looking at network convex area over here on the y-axis and depth over on the x-axis. And so essentially, as depth increases, we expect that like you're covering more area. And what we can do from this is be like, oh, we can infer root shape. So 4-inch collard, that really big, really deep one sits over here. Georgia is less deep, right? It's closer in depth, right, but not covering a lot of area. Sort of maybe 16. Fuzzy's cabbage collard over here on the left side of the screen is not deep at all, but it's covering a lot of space, right? So able to sequester nutrients and water in a way that make it a little different. And then finally, we got William Alexander getting down the bottom. It's not really doing much spread or yeah. And so we can begin to kind of categorize these in terms of their shape, right? Is what we can begin to do and look at potentially breeding some of this. And so this was an early first experiment where we were like, are there differences or are these guys just putting down roots that all look the same? And I think what we came out with, I'm not showing you all 17 varieties, all 18 varieties, but what we came out with was like there are definitely shade differences that we need to exploit out of it. Cool parts, right? The last science piece of this is that we had a lot of help and we did more than grow seedlings, right? So we were able to get some scientific data from this, which was cool, right? Helpful for the people. But then we were also able to do a lot with getting people involved with science. This is my baby. He was out doing some work with me. And this is really just to show you that it was more than just the science, right? There were people involved at each step of this process. So like I said, this is a picture of me and my baby. This is some of the second and third graders that we worked with our Jackie Joyner Kersee Center, so getting them to grow collards while we're also doing some of this root work in the lab. Right? These are some of the students out of the JJK that got a chance to come out and see some of the work that we're doing. I mean, there's some of the field experiences. This is one of my third graders. So on like the last day, we were looking at the collards and realized that they had gotten aphids. I'm not sure how someone was able to get those aphids, but right. We took that as an opportunity to put some of the aphids in a leaf in a petri dish, and we were taking pictures of some of the leaves. And so our third graders were up on everything from like glucosinolates and antioxidants and collards to aphids and pest pressure, right? Yeah. So all of this was opportunity to expose the students, right? There's students from our high school internship program that my colleague Curly Taylor runs, amazing program, who were able to come out and help when we were doing some of the leaf sampling for this project, right? And I think by and large, this really played into this idea of like, yes, we can do science, but also we're using people who have ways of knowing around these crops that don't look like the traditional university setting, right? And I think that was really cool. So from here, right, we had tons of people involved. We got these root traits now. We look a little different. Now we need to take it out to the field, right? Is the next thing that we did. This is more or less what we'll talk about the JJK fan and some of our new facilities. So yeah, saw that these guys are different. Now we need to go out to the field. And so this is that passive solar greenhouse that I was talking to you about earlier. Like I said, 11,000 square feet total. It's the first one used in the U.S. and it's expected to give us 30 to 35,000 pounds of food production a year. Of course, started growing season on through the rest of the season. And so we had this new facility and we're like, well, we need to put something in here. I was like, oh, I got collard greens. And so we ended up taking these collards and building out a field trial to look at the roots in this space. So we decided, let's grow some collards. So we took about 2 weeks growing our collard seedlings in the greenhouse in trays. And then we filled that entire 11,000 square foot with collard greens, right? It was a randomized blind experiment. So they're all placed in different places and we're watering them throughout a 60-day period. And waiting on them to get nice, full, and bushy. And then we go dig them up. Right? Fun part. So we did a good old shovel-omics experiment. We never heard of shovel-omics before because you've heard. But essentially, it's that root crown excavation technique that I was talking about earlier in the presentation. So we had the opportunity to go dig roots with a plethora of bird seed families, and we appreciate Jonathan seed families. And it was an amazing time. We're out digging collards in this space. Show you a couple more pictures here. So the idea is the first thing we wanted to do. Now we have this 11,000 square foot space filled with collards. One of the first things we wanted to do is score them. Shout out to Nick Speed, the George Washington Carver Farms in the back. He came out with one of his students and helped us on the farmer side doing some of the scoring. So we're really interested in agricultural traits above ground, like yield, right? So if you're a farmer or a gardener, it's just not enough for you, right? It's marketability, right? If you're going to sell these, do you think on a scale from 1 to 10, the people that you're dealing with actually want to buy them, or would it not look like what they want? And so scoring them was one of the first things we did. We went out, used a bunch of folks, like I said, a ton of help. The next major thing we wanted to do was get the weights of these. So we selected certain plants, sort of harvested the leaves and got weights on them, right? That gives us the opportunity to figure out, once we get the root information, we'll be able to tie that with how much above ground production was there. But there's time to dig. There was a lot of digging. I figured, since this was not like a big field, space, like acres and acres of field, the digging roots was not going to be hard. It was hard. You dug a lot of roots. Shout out to the team at our grow facilities. Rob and Marco did an amazing job. Kelly, thank you guys. I don't know if y'all were watching, but they were out there. The Rise Up guys from the External organization. This would not have been possible without all hands on deck digging roots. We have some fun points too, like shout out, special points if you can find the one of this buried in there and make sure that the roots. But the roots essentially come out dirty like this, right? And that's no good. No bueno. You cannot image those because it's got a lot of soil on it. And so we spent a lot of time making a muddy mess, washing soil off of the roots. Which is fun for kids, by the way. I took my son out to do this and he loved it. He thought we were in Smash. But so essentially we're digging these up, rinsing them off. They get clean like this. Awesome picture. And then it's time to do some analysis, right? So we got the roots. We set up we got tons of roots. Let's see, 3 to 500 or so roots. But I'm still analyzing data for Maybe is watching. I'm analyzing this. So now we have all these roots, right? And we need to take pictures. So we use this big digital photo booth. It's about the size of this phone camera on its side. Essentially, it's got a light on the back. And we put the roots in, and it gives us essentially a black and white image of the roots. I had some awesome students, Zakia and Karima, in the first picture, the high school interns, to come out and do some of the full day of like digging, washing, imaging, digging, washing, imaging. It was a lot of fun, and I think the ways that the community and the people who were involved in this project really had the opportunity for buying. I think going forward, that's the type of work, right, where the community has applicable input as a collaborator and not just an output of our outreach initiatives. So the best part was we gave away over like 500 pounds of Collards. Let's assume here you can see the size of the leaves. Like these were Collards. They were like a pound and something or a pound and a half of like lots of collard greens. So it's really dope. We were able to give some the food pantries. We were also able to give some to the families over at the Community Center. I mean, everybody was excited. They're like, "Oh man, you doing this food stuff? That's awesome. When can we get Collards?" So, some fun books buying for the science based on the food and the acknowledgement of the ways of knowing around this place, right? I think which was really cool to see because other things I've worked on. Okay. My mom's like working on the friend that you were working on. Like, I knew it's good. You're like, it's in your toothpaste and your charge, some of the sodas. Whereas this is like, hey, here's some collard greens you can have. So that was really cool. And so from there, next steps, right? We are beginning to analyze some of these roots. And so basically, we take them, we do these pictures. This original image on the left, the black and white image, is what kind of comes out of that photo booth. We send it through a very nice set of computational tools that are able to read those images and say, well, this root is longer than this one. It has this many tips. It has this many. So there's a ton of traits that we're looking through. And as I said, community's watching, we are working on it. But the cool part about this that I think, right, is there's some really cool patterns emerging, right? Go with me, my science corner. It's cool. So one of the things that we took is the average fresh weight, right, when we were doing these images. And so we would take the plants, weigh them, and say, well, this variety has this weight. This variety has this weight above ground. I overlaid that with some of the user rating data, so scores 1 through 5 for each of the varieties. And I think it's pretty cool that you can see like a trend that follows like the fresh weight that we saw here in St. Louis ties in pretty closely to what the farmers and gardeners were seeing across those 250 different sites when they did the original trial in 2020. I think that's pretty dope because there are root traits that we know are associated with. And so with my farmers who have no fancy equipment, who are just going out being like, this one is big, this one is small. If they can kind of guesstimate, more or less things like fresh weight, are they able to inadvertently select for root traits when we do these breeding experiments based on what they're seeing in the field? I don't know that yet, but I think it was pretty cool that this follows it fairly closely, right? And so with that, we'll talk about next steps, right? So what's coming next, right? So you probably saw the pictures of my son and some of the other students after Jackie, not at the Air Force Center. We were actually rolling each of these collards out after we selected which parents we should use, and we were setting them up on blind dates essentially and mating them together. At least that's the way I explained it to the kids. And so what we did was we got a bunch of the kids from these, the F1s. And so we're going to take these kids that we put from these crosses that we saw, based on the differences in root structure, and we're going to take these out to the JJK and grow them as well, right? Some of our community partners and some of the students that are out there. Basically, we want to be the roots again. So we get everybody in the room like to come be roots with us. And so as part of my PhD work, we'll be doing some of the roots there, and then we'll sequence them. We'll do 23andMe on each of these, and from there we'll figure like, oh, like this particular shape comes from this parent. This particular shape comes from this parent, right? It's a good way for us to be able to tie some of the genetic components to what we're physically seeing, right? But beyond that, we really want to get more farmer and gardener input. And so essentially the original variety trial that happened here in 2020 didn't include Missouri at all, right? And not because Missouri wasn't, supposed to be included, but really didn't have any participation from farmers or people. And so I would like to change that going forward. We really want to work with you all, work with people who are farming, who are already in this space, and see how can we take these seeds out and begin to selection with you and this together. Right. So with that, if there's anybody at all in here that's interested in sort of coming through and doing some of the things Kendra doing, would you mind scoring these, growing these out on your space, scoring them for things like seeds, flavor, yield? Please scan the QR code. It's not a lot of work, but we are going to add people a couple of things. It's pretty easy. We're going to use seed links, so have on your phone, or you can grow these and just kind of let us know what you're seeing, and those will be incorporated with the root data. I think this is important because I think seeds are more like living history books of human plants interaction, and so it's kind of like that banned book list, right? If we only allow specific people to do the breeding work, then we'll lose some of the things that might be indicative to us creating a more sustainable system. Aside from that, we're going to look at
11:50.
okay, all right, my bad. So I think just to kind of talk about science, right? I got nerd out about a lot of this. It's one of the dope side quests of this project, right? When we were doing some of the one of the dope side quests, because we're a root lab and we use X-ray tomography, some of the work that we do. I got to work with Keith Duncan some when we were doing some of the breeding pieces of this. So what you're seeing here is one of our collared flowers before it opened. I had to breed these by hand, basically. So we go in, take the pollen from the flower of the male that we were interested in, taking it to the female, pollinating, developing it by hand. Not fun. And so Keith got really interested when we were talking about the island effect in some of these spaces because it has an impact on pollen. And so we were looking on pollen and some of the reproductive structures within the plant. So we ended up taking some of these, just kind of doing some X-ray tomography, really seeing like any differences that we can see. So that was pretty cool. I think there's some more stuff that we're going to explore with Keith. And then second really dope side. Really dope side quest that we got to go on was like adding robots to some of this. 11,000 square feet. It was not fun to actually go out by hand.
Yeah, probably should.
Hard to see the robot movement, but so essentially, this is Garish Krishna from University of Champaign, and he studies autonomous robots. So he brought some of these robots out to the solar greenhouse. And we were able to do like a first pass of running the robots through some of the rows and seeing if they could pick up things like varietal differences, right? Can we train a model for it to be able to do that? Can we train a model for it to be able to identify pest pressure or disease pressure early, right? It's been like a big playground for me. So, but like my community is also watching, we're like, oh, so you were also doing all this. It's not it's a next. But I thought it was really cool because there are other people I think who are seeing the space of the JJK as a big playground, and I think that's essentially what we to be, right? It's a place where we should be exploring things, where you have something that is traditionally outside of the space and you can come and use it in the space, right? So shout out to Keith and Dr. Krishna for coming in. That's right. So this is essentially the end of my talk. And what I really want to do is sort of leave you with some hope at the end of the tunnel, right? George Washington Carver used to say, essentially, let me paraphrase, if you spend enough time with something, it begins to talk to you, right? Sort of the way he described it. This is a field out in East St. Louis behind one of the Lansdowne Up buildings. And before we finished the passive solar greenhouse, my PI and some of the committee members were like, no, a greenhouse doesn't show up right, or what happens if there's a problem, we should just go plant some of these collards out in East St. Louis in the middle of the field. So we tilled it up. There's all sorts of stuff. We were hidden in the soil. There were like old cassette tapes, old mixtapes, Britney Spears. There was a lot of stuff. And so we planted out this field experiment. Each of those 18 to 20 varieties of collards, maybe 10 to 15 times a piece, so huge experimental space. And then we just allowed it to grow. Originally, this was brown and there was no green in there. And it quickly dawned on me that, like, I don't have the capacity to go and weed this field. Like, I don't have it. So I was like, okay, I guess the weeds are just gonna have to be here. And then after that, it dawned on me that, like, I don't have enough time to go water this every day. Like, this was like 2 or 3 hours worth of watering during the day. So you had these little setups for the next day. And so essentially what happened was the passive solar greenhouse ended up getting finished on time. We were able to plant there, and I left it so long, right? And I think the beautiful thing that I was able to see in this was that, like, the plants, there's lots of plants in this picture. The biggest things you can see are the collard greens, right? And I think that was really impactful to me. I don't think I watered these. They're still there now. I stopped watering these in October. It was like October 15th when we planted them, and they didn't water for like 2 weeks. And they've just kind of been going on their own. And I think it was really impactful to me because it was, it kind of gave me the message that it's like the environment won't always be ideal, right? There's going to be tapes in the soil, might be a toilet seat somewhere. You won't necessarily get all the water that you need. There will be weeds, and you should definitely grow in spite of the weeds. So with that, that is my time. Thank you. Thank y'all for listening.